Yeah, it doesn't Also, there's one thing it's another thing to like intellectual quality of the music itself. Come on, bro. Also, yeah, ask yourself if games of low quality are really.
Alright. So just a couple things real quick here before we get started. Number one, I have to cancel my office hours today, as I mentioned on Piazza. Unfortunately, I appear to have caught a plague for my children. So, yeah, you probably want distance. I will be on Piazza to answer questions and so on. So, don't worry. It's not like there's no help at all. The other thing I wanted to remind you of is don't forget you've got pretty much a quiz every week from here on out. It's only 3 quick questions, so it shouldn't take you too long. There was one last Friday. There will be another one again this Friday. The one this Friday is on scheduling. Okay. So, that being said, our operating system of today is one that you may have heard of and may not. So it's called OS2. Anyone heard of it? Nobody. All right. Well, so OS2, and going with IBM's terrible naming system for operating systems, and obviously part of where our OS gets its name from, stands for Operating System 2, and it was released to go with IBM's computer known as PS2, not to be confused with a PlayStation 2, nor to be confused with the PS2 port on the back of your computer, which nobody uses anymore. This was actually this little ugly gray box with some turquoise and purple elements to it. Yeah, a personal computer. I used to have a bunch of them under my bed when I was a kid. Don't ask. It's probably best you don't. So, when IBM, this was kind of another one of those Microsoft IBM joint developments. It was released in 1987, and it was always meant to be an upgrade to DOS. So remember that DOS doesn't really do much. It has no concurrency or support for that at all. At the beginning, it didn't even separate privileged from unprivileged code. Everything just ran with privilege. It didn't use virtual memory or anything like that. Limited file system support, no desktop environment, limited piece of garbage. It worked. Anyways, OS2 was meant to be an upgrade to that. So IBM and Microsoft brought out this operating system that had a full desktop environment that was mouse-driven. It also had a bunch of other things. It had DOS with protected mode. So they actually separated, kernel and user privilege out. It had virtualization. It had all of the features we would expect. It could even do some multitasking. It could support up to 64 CPUs. Although in 1987, you probably didn't have that many, at least if you were a home user. I think the most I ever had up until recently was 2. That was in the 90s. And then it was because IBM realized that people were really dead set in their ways. They really, really liked DOS, and they really, really liked early versions of Windows, which we'll talk about another day. And they wanted to make sure that anyone who was considering OS2 wouldn't lose the application support they already had. This is one of the big things when you're trying to convince somebody to upgrade an operating system. This is why Microsoft has a really hard time stopping support for older OSs, is because people are terrified of losing support for the software that they use every day. So OS2 was designed to be compatible with all DOS and Windows applications. So if it worked in one, it should work in the other. Now, it was Windows' competitor, and the reason why you haven't heard of it is because it obviously lost. It did end up being rather popular with some businesses, and where you actually see it used most is with POS devices. Now, a little side story about POS devices. Once upon a time, I had a co-op where I wrote POS device drivers. And I did not know what POS device meant. I thought it meant piece of shit device. Because to be fair, the device was dumped onto my work desk as a pile of circuit boards that I had to assemble first before I wrote the driver for it. Of course, being a CS student, the only CS co-op they ever hired, I kind of gave them a look like, yeah, I'm not an engineer, but you run with it. They never told me what POS device meant. It doesn't mean piece of shit. It means point of sale. Piece of shit is still funnier though. Yeah, so why do they use it in POS devices? Because OS2 is actually a fairly small operating system, and so that actually makes it really good for doing embedded jobs. Why did it lose to Windows? Well, because it's terrible. So my high school is in the middle of nowhere, and we always had a dropout problem and a fail-out problem and all these things. And so for whatever reason, the government liked to throw money at my school. And so we had all this crazy internet stuff. We had satellite internet in the 90s. We had like T3 lines. We had more computers than anyone could ever possibly want. And they were like top of the line systems. And as part of this, we had different labs running different operating systems. And one of those labs was an OS2 lab. And nobody touched it because nobody could figure out how the hell to use it. Now, I'll show you a picture of it. This is OS2 War, which is actually the one that I've used. It doesn't, if you look at this, with the amount of computing experience you have today, I'm sure that you could sit down and figure this out. It's not that easy though. I always found the UI to be very cumbersome. And the thing that I found difficult was it was never clear where you were supposed to go to find a particular application or how you were supposed to launch that application. And if you compare this to Windows 3.1 or Windows 95, they were easier to figure that out. It was very obvious where you launch the applications from. It was very obvious how you get on Netscape. Now, I did use this a few times, but most people did not touch this lab. It ended up losing. Told you, not every OS we're talking about is a winner. So yeah, this is OS2 War in all of its GeoCities style background glory.
Why does your computer connect to a shredder?
Why not? This isn't my computer.
Okay.
It's probably one of those all-in-one office systems where it's like it can shred or it can do this or that. I don't know. Or maybe they just named their printer Shredder. That's a good name. If you like Ninja Turtles. All right. Don't worry, we will get to Windows and all those other OSs. It's just, they're fairly recent. So that's OS2. And we're done scheduling, so now it's time to move on to a new topic again. And this one is devices and I. So what's interesting is we've pretty much covered, we've got threading and concurrency and processes. We know how isolation happens and virtual memory. We know how we choose another thread to go next. So that's most of it, really, except a couple big parts. Where do you store this crap? And, if you have an operating system and you need to interact with it, how do you actually interact with it? How do you get information from devices and send information back to devices? So we're going to talk about devices and how to communicate with those devices. And then we're also going to move into how disks work and SSDs. And then the very last section of the course, we talk about file systems. So that's kind of fun. And yes, this is an area of OS I have a lot of experience with. I actually used to write printer drivers for Linux. Long time ago. So when you're thinking of a device, you're probably thinking of a keyboard or a printer or a joystick. Fairly mundane things. But devices are more than just the peripherals that we attach to our computer. there is in every single computer a device called a clock. And that clock is the clock that is used by your computer. There are also things like your disk drives. Those are devices. There are lots and lots of different devices that you can plug into your computer. If you have a little USB dancing flower, that's a device. Now, you could divide devices up into things like input devices, output devices, or combinations. And even OS 161, by the way, has devices. So in OS 161, we have a timer or clock. We need it. We have a disk drive. We have the serial console, which is what's responsible for taking characters and printing them on the screen. We have the text screen, which is for our character-oriented graphics. We even have a network interface, believe it or not, inside of OS 161. Not that you're going to use it to surf the internet. Now, some of these devices, like the clock, that's not real. We don't really think of that as so much as an input or output device. But a lot of these other ones are. For example, a disk drive. That is both an input and an output device because I am going to send data to it and we are going to be receiving data or retrieving data from it. But something like a keyboard, that is only an input device because I am only going to be taking data from the keyboard and into the system. Whereas a printer is a device that's only an output device because I am sending data from the operating system to the printer. We don't usually send data in the other direction, unless of course you have one of these printer scanner combos. So, if we're an operating system, we need to be able to get data off of this. Now, when we're talking about hardware and devices, there's a little bit of terminology that you should be familiar with. We often use the word bus, I usually refer to it as an address bus or the internal bus, but there's also something called a peripheral bus. A bus it's a pathway between different things. You can think of it as some wires that are connecting one thing to another thing. And we can pass signals along those wires if I want to send data from one of those things attached to the wire to another thing attached to the wire. So the internal bus, the address bus, or memory bus, or front side bus, it has a lot of names, is the primary bus that goes between the CPU and RAM. And it is very, very fast because obviously if we are trying to communicate with RAM, we want our interactions with RAM to be as quick as possible. So that is a very fast bus. And what's interesting is that many things are attached to that bus aside from just the CPU and RAM. Devices themselves are listening as well, and we'll look into that a little bit more later. The peripheral bus, expansion bus, whatever you want to call it, those are the pathways that are used for the devices to communicate with each other. And there are many of those. Then we have this thing called a bridge, which we don't really talk about, but if you're doing any extra reading, you may come across this term. And a bridge is just something that connects a couple of buses together. So for example, we may want a bridge between the address bus and the peripheral bus so that the devices can communicate with RAM, because devices need to communicate with RAM. Now, how do you actually talk to these devices? Well, as it turns out, every single device has a little teeny bit of logic inside of it. So even something simple, like this crappy keyboard, this has a little bit of circuitry inside of it. And as part of that circuitry, it has registers of its own. And what is going to happen is this little bit of control that's in this piece of hardware is responsible for receiving instructions from your computer, and is also going to use those registers to communicate things to the computer as well. So these registers have a name. They are called device registers. They are not on the CPU. They are on this. They are in every piece of hardware. If you have a disk drive, your disk drive has device registers. Those device registers are used for communication between the device and the computer. And they fall into three major categories. We have status registers, which are primarily going to be read, and they tell you something. For example, I may have a status register on this keyboard to indicate whether the caps lock is on or not. Then we have the command registers. Command registers we are primarily writing to tell the device to do something. So on a printer, there may be a print register. And if I write 1 into the print register, the printer will print whatever data it has. The last primary type is called a data register. And what's interesting about the data is the data register is both a read and written register, and it is a bigger one. It is used for the transfer of larger blocks of data to and from the actual device. Now what's interesting is even though there are 3 primary types, what you will actually see on a device is combination registers. So it's very common to have something like a status and command. If you read the register, then you get some information about the device. And if you write to the register, then you're telling the device to actually do something. And we can have data and command, and different combinations are possible. And I apologize, my voice is probably going to cut out by the end of this lecture. All right, so the best way to look at how these device registers work is to take a closer look at some of the devices that exist in OS 161. So we're going to start with the lovely clock. Now, every hardware manufacturer is going to need to make some table like this available so that you can actually build device drivers. Of course, OS 161 is a fairly open thing, so we have access to everything. So what this table is now, we're going to ignore the first 2 columns for now, and we'll revisit them later. But if you look at the clock, our clock in OS 161 has 6 device registers. There are 2 which should be fairly straightforward. They are the status registers that are telling us the current time. Now, they don't tell it to you in a way that you might be expecting. You're probably expecting them to say, oh, it is, I don't know what day it is. November 12th? 2019? And it's, 1:24 in the afternoon. No, that is not how the clock keeps track of time. The clock keeps track of time as the number of seconds, or nanoseconds, or milliseconds, that has elapsed since the epoch. And the epoch, and I never remember the exact time, is January 1st, 1970. So, and that is at time is UTC 0. That is the epoch, January 1st, 1970. Now this poses actually an interesting problem because we are storing the current time as the number of seconds elapsed since the epoch in a 32-bit integer. Anyone see a problem with that? It's a well-known problem, by the way. We're going to overflow it. And the date of the overflow is known, obviously, because we can calculate it quite easily. And it has been assigned the name, the end of Unix time. And apparently I signed up to go to a party in San Francisco. Because I will be alive when this happens, and so will you. So the end of Unix time, mark it in your calendars, is January 19th, 2038 at 3:14:07 GMT. Can you repeat that? So January 19th, 2038 at 3:14:07 GMT. Now this is going to be very much like Y2K. And I know, how many of you actually know anything about Y2K? Friend number of people? Some people are not too sure. Well, let me tell you a little bit about Y2K so you can understand why this is going to be an interesting problem too. So Y2K, up until the late 90s, people were storing the year as 2 digits. So if it was 1982, you would just write 82 as the date. And if it was 97, you'd write 97 as the date. The problem is when you get 00, does that mean 1900 or 2000? Because we don't know, and neither do you. So we will have a similar issue here. What do we do when we overflow our time register? Well, there's options. We can make that the new epoch. And I want to say that's a fairly simple change, right? We can just change our software. Or, we could maybe use 64 bits. Or, you know what? Let's see. That's almost 20 years away. Let people deal with it later. For the record, that's what the Y2K people did too. It didn't end up being that big of a deal. I know there were people who are like hoarding canned food down in their basement, thinking that the world was going to end. No, nothing happened. It was not exciting. It was totally boring. And I'm sure this is going to be the exact same thing. But you don't got to worry about it because it's not for another 20 years. Yeah.
Didn't they turn off the stock exchanges because they were scared for them? It was just like a computation error would happen or something?
I think so. I think I'd remember better because I was kind of like, I was in high school. It wouldn't surprise me because a lot of things like banking institutions especially used older hardware that would have been using the 2-digit date. So that probably would have hit them a little harder. And I know the banks and anyone who is still stuck on older hardware, that would have hit them a lot harder because it would have been like hard coded in the system to use the 2-digit date instead of. I don't think we'll have that big of a deal. All right, so we've got the current time. Now, that's not all your clock is there for. It's not just to tell you what time it is. Your clock is actually there for you to implement preemption. Right? Remember, in order to do this idea of time sharing, we have to be able to let a thread run for a short period of time and then kick them off involuntarily. We have to be able to throw an interrupt to make them go away. It's your clock that fires that interrupt. So, the clock, as part of its functionality, has the ability to do a countdown. And when the countdown expires, it fires an interrupt. To set that countdown, we have a number of registers. So, we have first a status and command register called countdown time. And when you write a value to countdown time, the clock will start a countdown for the time that you wrote. Now, when the clock is done, it's going to mark in the status and command register known as interrupt. It's going to indicate I finished my countdown and fire the interrupt. At which point, you can tell the clock, yes, clock, good job, I see you have done. You write that register to clear it, and then the clock can go about its business. Now, that seems like a very manual process because we would have to reinstantiate the next countdown. So our clock actually has the ability to, when the countdown expires, fire the interrupt, but restart the countdown on your own again. And we can do that by the command register restart on expiry. So if we write to restart on expiry, that will actually automatically restart the countdown once it is finished the first time. So what we generally do is we set our countdown time to be some smaller value than the scheduling quantum. So if our scheduling quantum is 40 milliseconds, maybe I will do a countdown of 5 milliseconds. And I will have an interrupt fired every 5, and then it'll just keep track of, how long have you been running for? Oh, this is your third interrupt? Okay, you can keep going. Now there's one more register that we have on the clock. And this is kind of a weird one, but your clock also has a speaker. And if you've never worked with an older desktop, you may never have encountered this, but every computer has a little speaker that used to be plugged into the motherboard, and there used to be a wire taking it from the motherboard right to the front where the little PC speaker was. That was actually controlled by a clock. It wasn't meant for playing music. It's meant for error beeps. So if you boot up your computer and there's some problem with the motherboard, there would be a beep code issue. And by the way, if you have a Mac, that is exactly how it does it. A lot of other devices used LED light patterns on the back of the motherboard to do it. If you write to the speaker device register, you will make the speaker beep. I do not believe this is working in OS 161, but you are welcome to try it. And you can annoy everybody in the lab or something. That was one of the funny things. So I used to write these printer drivers. And you're probably thinking that I wrote like laser printer drivers. No, I didn't. I wrote impact printer drivers, i.e. 9 and 24-pin printer drivers. And, well, mostly. And let me just say, open office floor plan, plus I'm writing drivers for the noisiest printers in the world. I like to make them make music. It's trying to find the perfect image to print such that Jingle Bells starts playing on a printer. Gotta annoy your coworker somehow, right? All right, so this is the clock. And it's fairly straightforward. So let's look at another one. Now this one is the device registers for our serial console. So this is getting characters from the keyboard and taking them and putting them on the screen or on the console. It has only 3 device registers. There is a command and data character buffer, and that is actually if you write a character to the character buffer, you would be putting, and that would be telling the serial console to put this character onto the console. And at the same time, if we are reading from that, then we would be getting any characters typed at the serial console. Now, here's an interesting thing. If I am trying to write to the serial console at the same time that someone else is trying to read from it, we're going to have a problem. How do you do a read and a write at the same time? How do you do 2 writes at the same time? When you try to tell the device to do something, it doesn't magically happen instantaneously. It takes time because the device actually has to physically do it. Which means it is possible for you to issue a write to the serial console and another write to be issued to the serial console while the first one is still taking place. What should happen? You know what the device manufacturers say? Undefined behavior. What does the undefined behavior mean? They don't know, and they don't care. That's your problem. Stop doing stupid things. So undefined behavior means you may get half of the character from the first one plus half the character of the second one. It means total garbage could be output. It could even mean the device catches fire. Undefined behavior really means anything could happen, and the device manufacturer is not responsible for it. So to help us with this, we have 2 status registers called write IRQ and read IRQ. If a read is in progress, there will be something in the read IRQ register. Likewise, if a write is in progress, there will be a particular value in the write IRQ register. And when the read or write has completed, there will be a completed message in the appropriate read or write IRQ register. And then it is up to you, the device driver writer, to make sure that you use synchronization and to prevent reads and writes from happening at the same time. That is why those registers are there. Now, remember, IRQ means interrupt. It's just one of those weird acronyms we have. All right. So you've seen kind of the types of device registers that we actually have. So now we actually need to write the driver. write the software in the operating system that is responsible for communicating with that device and telling the device to do something. So let's have this our first attempt at writing a device driver for the serial console. And I want to write, I guess. I want to write some characters. So, because I know that reads and writes on the serial console can only happen one at a time, I'm going to have a binary semaphore to offer mutual exclusion on the device. It is important that you use semaphores, and we'll discuss that shortly. So, we're going to PR device semaphore, and then I'm going to, I know that I have mutual exclusion on the device, so then I am going to write the character I want to put onto the serial console into the character buffer. And then I need to wait for the serial console to be done the task that I asked it to do. So what am I going to do? I am going to, in a while loop, repeatedly ask the device, hey, are you done? By looking at the contents of the right IRQ register. So I'm going to sit there. Are you done? Oh, no. Are you done yet? And when you're done, because that special value is in the right IRQ, it's finally safe to release our semaphore and another write can happen. This is called polling. We don't generally like to poll things. You know, there's an easier thing that we could do. You know, we have interrupts, right? And devices throw interrupts anytime they do anything. They're annoying toddlers. So we could rewrite that same device driver without polling by simply splitting it into two parts, which is going to outline why we actually need the semaphore and not a lock. So we have the device driver. We P the device's semaphore, and then we write a character to the character buffer. That's it. That's all I do. I can return, or I can block and wait for this task to complete while letting other threads go about their business. And then when the device is done, it's going to fire an interrupt automatically anyways. I have an interrupt handler in the operating system, and the interrupt handler is going to write to the IRQ register to acknowledge that, yes, good job, device. I've seen that you're done. We clear out the interrupt, and then we can safely release our hold on the device. Now, why do we have to use a semaphore and not a lock? Because the thread that executes the device driver is probably going to block and go to sleep while it is waiting for this task to be completed, which means that the thread that is executing when the interrupt comes is never the thread that instantiated the contact with the device. So if I had a lock, it wouldn't work because locks can only be released by their owners. And so we can use a binary semaphore instead because we don't care who the owner is, but we still have mutual exclusion. So that is a better way that we can do it. Now, some interesting things about device drivers. So you might be thinking that there's no devices out there at all that uses polling. No, actually, USB devices use polling. And my understanding of the USB implementation, keep in mind I'm not a hardware engineer, is that in order to have USB devices throw interrupts, they actually need to add another line in the cable, which would change the whole specification and everything like that. So, or the interrupt would end up corrupting the data that was coming in on the regular USB bus. So, since they didn't want to add any extra lines to support interrupts, and they didn't want interrupts corrupting the data that was coming in over the USB line, what they decided to do was actually do polling for USB devices. Now what usually happens is on your motherboard you have a USB controller, and it's the USB controller that is pulling the USB devices on your behalf, and then the USB controller could fire interrupts, or it can use continue the polling up through the system. So there are options. That's USB does use polling. So not everything uses the interrupt systems, but a lot of things do. Now, some other things, and you might be wondering, do device drivers run in kernel mode or in user mode? And instinctively, you're going to say these are kernel privilege. All of them. You're mostly right, except where you're not. In Linux, the majority of printer drivers are user privilege. So let me tell you a little bit about it, because I kind of know something about this. If you were to write a printer driver in Linux, what you're going to do is you've got to take the document and you've got to translate the document that you're trying to print into the printer's native assembly language, because printers speak their own assembly language. And if you're rich, you have a printer that speaks PostScript, and all you have to do is convert to PostScript. But most people don't buy those printers, and they buy just a regular printer. And so what you have to do in the driver, and this can happen totally in user space, is take the document, convert it into the printer's assembly language. And then it's simply a matter of taking that assembly program for the printer and sending it to the printer's port. And in Linux, all of those ports that your printers and so on are attached to are files. For example, I was often working with printers attached on a serial port. And so once I got my document, my assembly file for the printer, I sent it to dev tty1, which is the serial. That was it. I didn't have to write a single drop of kernel code to do that. That completely happened within user mode. Now, when I sent my file to the port file, yes, the operating system is involved, but I didn't have to worry about that. So the majority of device drivers are part of the kernel. And in fact, if you look at the code base for Linux or Windows or Mac, the vast majority of their hundreds of millions of lines of code is dedicated to device drivers. But there are some circumstances under which the device drivers don't actually have to be kernel privileged. And that's kind of fun. And if you're wondering how many of these printer drivers have I written, I have done a 9-pin printer and a 24-pin printer. I have also done 4 point-of-sale devices. So receipt printers. Handheld, things you get at the restaurant to pay your bill. Fun stuff. All right. So we've got device registers to actually learn about the device and tell the device to do something. We know how, roughly, with pseudocode, to create a device driver and an interrupt handler if we wanted to. But how does the data actually how do we actually communicate with these device registers? Like, do we have special assembly instructions that we are using to communicate with the device drivers? Because that would actually be pretty complicated. Because new devices are coming out every day. So how can I have hardware that is aware of every possible device? It's kind of weird. Well, there's actually lots of ways that our device drivers can access the device registers. So the first two options are generally used for smaller things, and they are port-mapped I/O and memory-mapped I/O. So the idea behind port-mapped I/O is we do have special assembly instructions. And what we're going to do is we have another address space. So outside of RAM, we have another small block of memory that we are addressing with fewer bits. And instead of calling them addressing, we're going to call them port numbers, even though each port number is technically an address in this very special region. And each of these ports can be mapped to a device register. And what's going to happen is we use these special instructions to read and write to the ports. And when we do reads and writes to the ports, the devices are watching that address line. And when they see a port number that corresponds to one that they are using, mapped to, they will know, oh, you want to talk to me, and you want to talk to this device register, and so they can grab the data or send the data to that appropriate place in memory. Now, this is a fairly fast method for doing it because we are closer to the CPU, but unfortunately, one of the downsides of using port mapped I/O is there are a very few number of ports because it is a much smaller region of memory, and the other downside is that it is not general purpose memory, which means you must use the special in and out instructions in order to read and write from it. You can't just use regular assembly to manipulate the values in it. If you wanted to manipulate the value in a port, you have to copy it into RAM, do regular assembly, and then copy it back. So it's a bit more of a pain in the butt to use. Now, memory mapped I/O. Well, wait a minute. Why am I using this special space here that's restricted when I've got all this RAM? So memory mapped I/O, what it does is it finds a region of RAM and says, this chunk of RAM, that's for device register mapping. Remember KSEG1? Memory mapped I/O. It is marking a small region of our memory that is going to be used for device registers. So what we're going to do now is every device is going to be listening to the address bus, the primary bus. And it knows which particular addresses in RAM it's supposed to be paying attention to. Like, oh, my speaker register is address deadbeat, for example. And it's going to see every single address that comes along the line. And when it sees deadbeat, it'll be like, that's for me. And it'll see, oh, you're writing to deadbeat. You want to send me data. And it will grab the data and take it to itself. Now, upside, it's RAM. There's lots of space, lots of flexibility, no special instructions required. Use regular assembly loads and stores to interact with it. Downside, every device has to translate every single address to figure out if the address is for it or not. Which means that from a performance perspective, memory mapped I/O is not as good as port mapped I/O. Now, what is your computer using right now? Both of them. We are not saying this is the old way and this is the new way. Nobody uses the old way, everybody uses the new way. No. When it comes to devices, everybody does everything. It's just like, I said, polling may seem like a bad idea, and yet USB uses it. Somebody's always using this stuff. All right. So here we go. This is OS161. So our devices, remember they map to the first 500, that KSEG1, and it maps to the first 512 megabytes of physical memory. Well, the only region of physical memory that KSEG1 actually uses is that little yellow chunk there, devices from 1FE all the way to 1FF to the end. The very, very end. There are 32 slots of 64 kilobytes each. Each device gets assigned a single slot regardless of whether it uses it all or not. So OS161's memory mapped I/O supports 32 devices. Now, I'd like to go back to this slide here where we are saying, discussing all of the different device registers. How do you know where in a slot each device register is supposed to go? Well, this chart tells you. The offset is the position within the slot where that register is, and the size in bytes that register is going to be within the slot. That must all be provided by the hardware manufacturer in order to actually implement the device driver. Although, for the record, most of the time, hardware manufacturers write their own device drivers. Don't use Microsoft's NVIDIA driver. Use NVIDIA's NVIDIA driver, right? All right. So that's really great for small transfers to devices. But what about a big transfer to a device? Because I'm not always thinking about, transferring a single integer. If I'm downloading a file of BitTorrent, I'm downloading, tens of gigabytes of data, and I want that data written to my hard drive, which means that I'm going to be sending large chunks of data from RAM to my disk. So there's got to be ways that are used for transmitting large blocks of data from RAM to disk, and there are, and they are called program-controlled I/O and direct memory access. So program-controlled I/O is very, very simple. The CPU is actually responsible for performing the memory transfer itself. So if I've got a 10 megabyte chunk that I want to copy from RAM to my disk with program-controlled I/O, my CPU actually performs the transfer itself. Now, there's a problem with that. The problem is that while the CPU is performing that data transfer, it's not doing anything else. Which means that all of my other threads which could have been running are now waiting for that data transfer to complete. We probably could have made use of the CPU's resources a little bit better, which is what direct memory access is about, or DMA. So what DMA does is DMA says, you know what? This device is connected to the address bus already. Wouldn't it be nice if we just let it do the transfer itself? So, and this is a very, very high level explanation. What we're going to do is the CPU initiates contact with the device and says, hey device, I've got a job for you. There's 10 megabytes of data and I need you to copy it. And the device says, all right. And now the device is going to directly communicate with memory and do the copy itself, which means the CPU is freed up to work on other threads. And then when this device is done, the device fires an interrupt to inform the CPU, hey, I finished my job. Yeah?
What if I wrote a malicious device that wrote stuff that I wasn't supposed to?
Yeah, that's doable. We have these things called keyloggers, right?
Yeah, like is there a way for me to prevent that?
Getting down into hardware security is, I want to tell you, yes, there are things that have been done to try to prevent malicious hardware from being inserted into machines. And I also want to tell you it's one of the most common ways for people to steal things. Installing a keylogger takes no effort at all, and it's pretty damn successful.
Okay.
It's also how I think there was something that happened with the US, I want to say, that they got some plans for something by some kind of hardware plant on a USB key. And I can also tell you that, so I work a lot with the film industry, and we are not permitted to have any devices on us whatsoever for fear of this. So, yeah. Fun stuff. Now, this explanation of DMA is actually not a really great one. DMA, what's interesting is DMA is actually a piece of hardware itself. So there's actually something called the DMA controller, and it has its own device driver. And the DMA controller is more directly involved with the transfer instead of the CPU, but we're not going to go into that. But if you're interested, by all means, office hours, I'd be more than happy to talk to you more about how DMA actually works. All right. Now, what does your computer use of these two options? Again, the answer is both. There are some devices that can only use program-controlled I/O because they don't support DMA. There are some devices where DMA is the only thing that is used. We still use port mapped and we're still using memory mapped. These are just some of the available options for us for communicating with the actual devices themselves. Some of them, the major ones. All right. So before we get into any more sophisticated device drivers, let's talk about a very, very important device for you. And that is a persistent storage device. Because obviously our operating system has to live somewhere. And we're not talking about the early 80s and Apple, where their operating system actually lived on a ROM chip. It's actually a pretty good strategy. Operating systems these days are multiple gigabytes in size. That has to live somewhere in persistent storage. If you go on the internet and you download something, and you leave an icon so the power goes out, you want that file to be there when the power comes back on. You don't want to have to keep downloading that file over and over and over again every time you want it. We need persistent storage. That is, we need the ability to store data without the presence of an active power supply. And what's interesting about persistent storage, and this is where the history geek in me kind of comes out, is that it's actually been around since like the 1700s. This is not a new idea at all. So the very first form of persistent storage goes back to those old weaving looms, the Jacquard weaving loom and such. They actually, when they were trying to weave these different patterns, you've got humans. Humans make mistakes. So they found a way to mechanize the process of the weaving loom, and they created programs for the weaving loom. Now, it's not somebody sitting there writing code because it's like 1740 something. It is a punched metal card, or a series of punched metal cards. And as these gears, they would have pegs that go through the different holes in the metal cards that would cause the loom to move in such a way that you get a pattern woven without human interaction. Those were the first programs. The first persistent storage was punched metal cards. And we ended up using punched paper tapes and punched paper cards probably through between the 80s at least. Now, another thing that we've used is magnetic drums. And that's actually a cool one, and magnetic tapes. Now, magnetic drums actually are an old form of solid state, which is kind of cool. But magnetic tapes is one you may have seen. Have any of you used a VCR? Or a cassette player, or an 8-track? Maybe you don't know what an 8-track is. So magnetic tapes is actually a really popular format of storage. And if you look at it, we've actually been using this since like the 40s. And these magnetic tape storage drives are these fridge-sized units. And they're great. It's a little piece of plastic tape which has a ferromagnetic material on it, which is used to store the orientation of the magnetic field as being a 0 or a 1. And it's super popular. Now, what's really interesting about magnetic tape storage is that we still use it today. And you might be thinking to yourself, why the hell are we still using this today? I can even tell you that this very university still uses magnetic tape storage every day. And the reason why we are still using this every day is because for archival purposes, it is the cheapest way to buy storage. Because the last time I looked, you could buy a terabyte for like 10 or 15 bucks. And I'm sure if you're buying it in volumes, like this school does, or like the film industry does, you could probably get it even cheaper. So a little magnetic tape that's a few terabytes is a fraction of the price of an actual magnetic hard drive. Yeah.
How big physically is a terabyte of this tape?
So the last time I saw one, I saw a 1 terabyte Sony tape. It's about that big.
Wow.
It wasn't very big.
Like a wheel of it?
Yeah, it was just a little thing like that. Yeah.
For practical purposes, how long does the tapes last? Doesn't the magnetism decay?
So this is one of the big problems with magnetic tapes that we still have to this day. They're very volatile. So there's a few things. Number one, after about 10 to 15 years, depending on the quality, the tape starts to stick together. And you have to put it in this kind of makeshift oven thing to try to get it to come apart. And then usually you do that for the sole purposes of making a new copy. I have actually done this for film archives. It's kind of fun. You reel out these older giant reels of tape and you get them so they're not stuck to each other anymore, and then you make a new copy. But that's actually one of the other problems about their volatility is the more you use them, the more degradation of the field there is, and so the noisier and the noisier they get. So if you've ever had a VHS that you really, really liked, and I know when I was a kid, like I couldn't afford to buy Star Wars, so I taped it off TV. And the problem is after about 5 times of watching it, the tape is actually so grainy that you can't use it. And that's one of the things you get is bit rot with magnetic tapes is a pretty big problem. Whether it's the medium itself altering or it's, radiation from space, which yes, that is a real thing. The sun can flip bits. The other thing, like I said, is just the more you wear it, it does wear down. So it is a bit of a volatile storage thing. But at the end of the day, that's what they like to use. And it still ends up being cheaper than doing discs, like actual physical discs, unfortunately. Yeah.
What's the transfer speed for these magnetic tapes?
I actually don't know, because I don't think I ever looked at it. But it's not, I don't want to say it's great. Like if you wanted to find data on a magnetic tape, it's a linear search. You actually will have to, fast forward the tape to the correct position to get it off. And that's one of the problems that people had back in the 40s and 50s and the 60s is in order to get data on and off of these tapes, you had to actually move the tape to the right position. So if you look at old programming languages like Fortran, they actually have fast forward and rewind instructions. And nowadays, they don't physically move tape, they move the file pointer. But that's where they come from, that's why they're named that way. But yeah, I'm not sure about data transfer rates for them actually. All right. So another thing we use is floppy drives and hard drives. Floppy drives are kind of like a magnetic tape, except it's a floppy piece of plastic that's in a hard case, sometimes. And a hard drive itself is also another piece of material that's covered in ferromagnetic substance. Then we got CDs in the 1980s, which are kind of like records taken to the extreme. It's an etching on a surface that's read by a laser. Again, and DVDs and Blu-rays are all roughly the same technology there. The problem with them is any kind of scratching or noise on those surfaces is going to impact the ability to recover the data. Then we've got solid state memory, which we think of SSDs as being new, and they're totally not new. We had methods of doing solid state storage back even in the 50s, which is kind of cool. But it didn't look anything like it does today. And now we have another thing called resistive RAM or ReRAM, which has come out in the 2000s as well. So persistent storage, there are lots and lots of different options through history. We're going to start by talking about hard drives. And I know many of you probably don't use hard drives anymore. And so we will also talk about SSDs and ReRAM as well. So let's look at your good old hard disk here. So if you were to open up your hard drive, and please, for the love of all you consider holy, do not open your hard drive. This is a very, very bad idea. But if you were to open it up, what you would see inside is a bunch of circular platters, and then an arm, and attached to that arm would be a bunch of these read-write heads, one for each and every platter. I know there's only one drawn there, but there would be one for each of those platters. Now, those platters are made not of plastic or metal. They are made of porcelain or glass. Your hard drive is very, very fragile. If you drop it, it may never work again. Those platters made of ceramic and glass and porcelain are covered in a ferromagnetic material, and it's that material that we're altering the magnetic field on to encode as zeros or ones. Now the read-write head, which is going to be actually the surface we use to read or write data onto those platters, it is not sitting on the platter. It sits a few microns above the surface of the platter, and it can never touch. If it touches the platter, you get something called a head crash, and there's a pretty damn good chance that your disk never works again, because it will damage the surface of the platter itself. I've had this happen to me. I had an old laptop. It was the middle of the night, and I started hearing this ka-thunk, ka-thunk, and I was like, what is that sound? And then it's like your heart just sinks. You're like, oh no, my disk is dead. And it was the middle of my last term of undergrad, and I had an assignment like 3 days later, which I had to start over because when your disk is dead, yeah, how do you get your data off? You can, but you gotta pay. All right, so what's going to happen is our data on our disk is actually laid out in a specific manner. So what we have, and this isn't necessarily the greatest, is each platter is divided into concentric rings called tracks. And each of the tracks is divided into segments. Each track has the same capacity as does each segment, even though the diagram here would suggest otherwise. We also, for simplicity's sake, will tell you that every track has the same number of segments, just to make it a little bit easier. When you want to read or write something on your disk, we do two things. We have to move the read-write head to the correct track. So we're going to move our read-write head to the correct track. And then we're going to rotate the platter so that the correct sector is underneath the read-write head. Now we don't let the read-write head read the whole sector at a time. No, the read-write head can only read one bit at a time. So we actually usually have to continue rotating the disk underneath that read-write head so that the head can actually read each of the bits in that sector. When I call these, so these disks are both fragile, incredibly fragile. They are also very slow, because when you're trying to retrieve data, things actually have to move. So as a little bit of fun, I thought I'd show you some fun videos that will show you exactly how they move. And another video which will show you just how fragile these are. So I'm going to go, I will post these to Piotr as well. So this is also known as people who have too much time on their hands. So the first video I have is a floppy drive, which have the same rough idea, but instead of the read-write head moving like this, it moves just in and out. Yeah, it's fun. There you go. Floppy drive. Yeah. As I said, this guy's got way too much time on his hands. thing. If you don't like Zelda, I'm sure he's got whatever video game. I'll post a link to it. So this is how the floppy drives move. So let's look now at how the hard drives move. Yeah.
So, in terms of controlling that device, would he be sending a signal to tell it what bit of memory to access, or is he directly controlling the ARM?
I'm not quite sure how he does it. If I were to do it, what I would probably do is I would figure out which positions in the disk and how long each of the writes need to be so that I could get that sound. Because you don't get a lot of sound from the rotation of the platter. You get most of the sound from the moving of the actual read-write head entities. So that would be the motor you're actually hearing is the seek, the read-write head. So I would be looking at placing my writes in positions that are going to cause that read-write head to move the distance I want it to. Yeah.
So like the idea of a hard drive seems really like silly to me. Like, who comes up with that idea? It's very like the idea of like metal platters and spinning stuff. Like, how was that invented? I guess.
I actually don't know how it was invented, but I mean, if you look at it, things like the gramophone and the record player are a similar construct, right? We have some kind of data on a rotating device being read by some kind of armature. I don't know if you've ever used a record player before. It's roughly the same idea. Yeah. And my guess is that's where the inspiration actually came from. All right, so regular hard drives now, you'll see the ARM moves a little bit different. Again, somebody with way too much time on their hands. This time it's Radiohead. There's a array of hard drives.
Is that the motor, or is it scratching the disc?
That motor, that's the motor. That's what's touching the disc. The motors actually make a fair bit of noise. And it's probably not something you've noticed too much because the discs that we have today are actually quite quiet. But I remember the discs that I had in the 90s, you could hear them on the other side of the room. And it wasn't actually because it was scratching the surface, it was simply loud motors. And the floppy drives were like 1,000 times louder. So that's how they move. And now I have one more fun video for you. This is something for when you go on co-op term. Please do not do this. Either your employer will either commit you to an asylum or they will fire you on the spot for being dumb. But it's good for experimental purposes just to show you this. If you want to know how fragile these things are or how sensitive they are, this video will show you. All right.
I'm Brendan, we're here in the Fishworks lab. Sorry for screaming, it's very loud in here with the air conditioners and servers all around me. We just made an interesting discovery and we thought we'd show you straight away. So over here I'm measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk.
So this middle one here, this is the plot I want you to watch. These are operations on the disk taking at least 512 or 520 milliseconds. And you will note right now, there's almost none. That's okay, there's almost none until he does what he's about to do.
This is using dtrace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. The lights are blinking on these JBODs because they're doing work. What I'm going to do is not recommended. This is not supported. Do not try this at home.
See the spike? That extra noise, that extra vibration is impacting the motion of those motors and their ability to complete the operations in time. You got to repeat the experiment, right? These drives are very sensitive. If you want to know why people wanted to move to SSDs, especially when we have laptops getting smaller and smaller, there's a very good reason why. And then other issues that you can come up with these disks is amazing. So I can tell you a story of a company that will remain nameless who wanted to make one of these arrays. And at the time they wanted to build something like, I don't know, it was 100 or so terabytes. And the tech guys had gone out, and the tech guys said to themselves, okay, we could get Western Digital greens for our RAID array, but oh look, the manufacturer says do not use with RAID arrays. And then they write about why, and they're like, oh yes, obviously that's a dumb idea. So they realized, okay, we'll get WD blacks or WD reds. And they took it to their finance department, and the finance department said, that's nice and all, but look at these greens, they're cheaper. And the IT guy says, no, it will not work. And the finance guys didn't listen, and they ended up buying greens. And the IT guys put their hands up in the air, and they said, okay. And here's what happened. Green drives like to go to sleep because they're supposed to be the environmentally friendly kind of drive, which means that they spun down. Now, one thing you may not know about your hard drive is that your hard drive is always spinning. It doesn't just stay stationary until you ask to use it. No, because the problem is the spin up takes time and spin down takes time. So your hard drive is actually constantly spinning. Except for these environmentally friendly drives, which when they detect a lull in communication with them, do spin down and go to sleep. The RAID controller interpreted that as a disk failure. And when you've got 100 or so of these doing it, after about 3 failures, guess what the RAID controller says? The whole array is gone. And it was just because it was these environmentally friendly disks. So the company had to go out and actually repurchase all of these disks all over again. Disks are interesting, shall we say. So just to give you a hint as to what we're going to do next class. Sorry, no fun videos next class. Next class, we are actually going to look at how to calculate the cost of doing a read or write on a mechanical hard drive. And then we'll look at disk head scheduling and then SSDs as well. All right, so that's it.
You're just going slowly, don't yell at me.